Good morning. I'm Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, I'll be discussing about the allotropic forms of carbon, that is two allotropic forms which are graphite and fullerene. Now, if we see in detail the allotropic forms of carbon, then carbon can be divided into either crystalline or amorphous part. And the crystalline forms of carbon are diamond, graphite and fullerene, whereas in amorphous form, carbon exists in the form of coal, charcoal and lamp black. So first I'll be focusing on graphite. Now coming first to the structure of graphite. The graphite is composed of flat two-dimensional sheets of carbon atom, and each sheet is a hexagonal set or a net of carbon atoms, and it may be regarded as a fused system of benzene rings. These layers, they are held together by weak van der Waals forces. The graphite, it exists in layers, and there are weak van der Waals forces existing between the different layers of graphite. The carbon-carbon bond length within the sheet is 1.41 angstrom. Each carbon distance between the two carbon atoms is 1.41 angstrom, and the distance between the sheets or the layers is 3.35 angstrom. The difference between the two layers, adjacent layers, is 3.35 angstrom. The interlayer distance is larger than twice the covalent radius of carbon. That is, 2 into carbon single bonds carbon distance is 2 into 1.54 is equal to 3.08, and this distance 3.35 angstrom is greater than this 3.08 angstrom. In graphite, only 3 of the valence electrons of the carbon atom are involved in the sigma bonding. Therefore, the hybridization is sp2, and the 4th electron forms the pi bond. If we now see the electronic configuration of carbon 6, so the electronic configuration is 1s2, 2s2, 2p1, 2py1 and 2pz0. Now, when they are involved in the sp2 hybridization, then it becomes 1s2, 2s1, 2p1, 2px1, 2py1 and 2pz1. And the carbon atoms in graphite, they are sp2 hybridized. That means 1s and 2p are involved in the formation of these sigma bonds. Now, sp2 carbon, you can see here that this carbon has 3 hybrid orbitals at 120 degrees angle in one plane. So these are the sp2 hybridized orbitals, and the difference in the angles is around 120 degrees centigrade, 120 degrees, forming the 3 sigma bonds with 3 such carbons, and a hybridized orbital is present at right angles to this plane. This is the pi orbital which is present, which is not involved in the formation of the sigma bond, and it is present at right angles to the plane. If this is the plane, then this pi orbital is present perpendicular to the plane. Now, each of these sp2 hybridized carbon, they combine with each other to form a sheet of hexagonal arranged network. Now, these dots are representing the carbon atom, and each carbon atom is bonded to 3 other carbon atoms by sp2 hybridization, and they are arranged in a network of hexagons. Now here, each carbon atom contains unhybridized p orbital. This is the unhybridized p orbital which is present on each carbon atom. So these unhybridized p orbital, they fuse together due to resonance, and they form rings of delocalized electrons. And these rings of delocalized electrons, half of it lies above the hexagonal plane of the carbon. If this is the carbon hexagonal plane, this is the plane, here there are the hexagonal plane, then half of the p orbitals, they lie above the hexagonal plane and half lies below the hexagonal plane. Here it is below the hexagonal plane and they are fused together. Now, coming to the types of graphite. There are two types of graphite. One is the alpha graphite and the other one is the beta graphite. Now, coming first to the alpha graphite. Alpha graphite is that graphite in which the layers, they are arranged in the sequence of AB, AB. And the third layer is going to be identical to the first layer. That means, if this is if this is the A layer, this is going to be the B layer and then again the A layer. The third layer, the position of the carbon atoms will be identical to the first layer. So, this is the alpha graphite, and the second one is in which the beta graphite, where the layers, they are arranged in the order of ABC and ABC. That means the fourth layer will be identical to the first layer. And the properties and uses. The heating turns beta graphite into alpha graphite. If you heat this beta graphite, it will get converted into alpha graphite. And if we grind alpha graphite, then this alpha graphite will get converted into beta graphite. Now, the bonding between the different layers of graphite, these different layers of graphite, it is very weak. Therefore, the graphite, it cleaves easily between the layer. That means the interlayer distance is large, and it accounts for the softness of the graphite. Graphite is soft because these layers keep sliding over one another as coefficient of friction is low, and therefore it is used as a lubricant. Now this wide spacing of sheet also means that the atom do not back together to fill the space very effectively. Therefore, the density of graphite is lower than the density of diamond. In the diamond, they are closely packed, sp3 hybridized structure, and in graphite, the layers, since they are quite apart from each other, therefore, the density of graphite becomes lower to density of diamond. Density of graphite is around 2.25 gram per centimeter cube, whereas in the case of diamond it is 3.5 gram per centimeter cube. And it is because of this that graphite molecules, they can slide over each other on application of force, and graphite, it is a smooth material. Now, since the carbon atoms, they are sp2 hybridized, they are covalently bonded. Therefore, graphite has a high melting point. It is insoluble in water and organic solvents. The pi electrons, they are delocalized over the entire sheet, and due to this, these mobile electrons of graphite, they can conduct electricity within a sheet, but not from one sheet to another. Since the pi electrons, they are delocalized with each other and they are going to form the rings, therefore they can easily conduct electricity within each layer. And graphite is thermodynamically more stable than diamond. Its free energy of formation is around 1.9 kilojoule per mole. So thermodynamically it is favorable for diamond to turn into graphite, but they do not do so normally, because there is high energy of activation required. For exciting the electrons in diamond, there is high energy of activation is required. The reverse process is not thermodynamically possible because it requires very high energy conditions, and graphite can be converted into synthetic diamond at high pressure and high temperature. The temperature is around 1600 degrees centigrade and pressure of around 50,000 to 69,000 atmospheres. And when an electric spark is struck between graphite electrodes, the soot is produced, which is mainly of carbon black, but it also contains significant amount of carbon 60, a carbon cluster compound which is also known as Buckminster fullerenes. Now here I am showing the structure of graphite. Here you can see the hexagonal rings which are formed in each layer and the carbon atoms which are sp2 hybridized. So these are the different layers of graphite, and these are the covalent bonds between each carbon, and the distance between two carbon atoms is of the order of 1.42 angstrom, and the distance between two different layers of graphite sheets is of the order of 3.4 angstrom, and there are weak van der Waals forces between each rings, between the sheets which exist. Now, the delocalized electrons which are present in the unhybridized p orbital, they are free to move anywhere within the sheet. Therefore, each electron is no longer fixed to a particular carbon atom. Since they are delocalized, so they are not fixed, and because of the presence of these free electrons, graphite is a good conductor of electricity, and since they are pi electrons, therefore it is also a good thermal conductor. There is, however, no direct contact between the delocalized electrons in one sheet and those in the neighboring sheets. Now here I am showing two different sheets. This is the layer of carbon atom, and there are delocalized electrons, but there is no connection between the delocalized electrons of one sheet to the other sheet. So the neighboring sheets electron, they are not directly contacting each other. Now the next allotropic form of carbon which I am going to take today is fullerene. Now this fullerene, it was discovered by Croto and Smalley in 1985, and in 1996 they got awarded the Nobel Prize for its discovery. So the 1996 Nobel Prize for Chemistry has been won by Harold W. Croto, Robert F. Curl and Richard E. Smalley for their discovery in 1985 of a new allotrope of carbon in which the carbon atoms are arranged in closed shells. And it was discovered during the experiment of laser vaporization of graphite rod under high vacuum chamber. And this is because the graphite sheets break down to form spherical fullerenes. These graphite sheets, they break down in an inert atmosphere at high temperature to form spherical fullerenes. And these allotropic forms, they are also known as Buckminster fullerene in the honor of architect Buckminster Fuller, who designed dome-like structures based on hexagonal and pentagons which resembles the C60. Coming to the structure of fullerenes, now these fullerenes, they have a cage-like structure, and there are different types, and they can have the formula of C60, C70, C78. All the carbon atoms in C60 are on the surface, and hence they are called buckyballs. The structure of C60, it resembles a soccer ball, and it has an icosahedron structure, and it is a made up of, that is, it is a polygon, and it is made up of 20 hexagons and 12 pentagons, with the carbon atom at the vertices of each polygon. At each vertex, a carbon atom is going to be present, and they bond along each polygon edge. The only restriction is that no two pentagons, they touch each other. I'll show you in this structure how no two pentagons, they are going to share the common sides. Now here you can see the structure of fullerene. In the center there is a pentagon, and the pentagons on all the side, it is covered with the hexagons. So there are 20 hexagons and 12 pentagons. So at each pentagon there are hexagons, and then only pentagons they come. So the pentagons won't share any of the sides with each other. The diameter is of the order of 0.7 nanometer, and there are 30 double bonds. That means there are 30 C double bond C. It has a face centered cubic structure. It is a semiconductor, and the pentagon sides in C60 are more strained than the hexagonal sides. Therefore, at high temperature, molecules breaks at pentagonal sides. So a soccer ball is a model of the Buckminster Fullerene C60. Here in the C60 soccer ball, you can see a pentagon in the center, then the hexagons, and then pentagons and hexagons. So this is a model of Buckminster Fullerene. Coming to the synthesis of fullerenes. Now these fullerenes, they are synthesized by vaporizing graphite rod in inert atmosphere, generally in helium atmosphere. Evaporation of carbon is done using resistive heat. When an electric spark is struck between graphite rod, in all the above methods, soot is produced, which is mainly carbon black and contains significant amount of carbon 60, a carbon cluster compound known as Buckminster Fullerene. Now coming to the properties. Now this fullerene, it forms a deep magenta solution when dissolved in benzene. That means fullerenes, they are soluble in organic solvents. It is very tough and thermally stable. That means we can use them at high temperatures also. It exists as a discrete molecule. That means a single molecule can show its existence. It can be compressed to lose 30% of its volume without destroying its carbon cage structure. That means if it is occupying this much of volume, then this volume reduction can be taken place, or it can be compressed. And if you are going to compress to, or if you are going to make it lose 30% of its volume, even then this carbon cage structure will not get destroyed. A magnetic fullerene has been formed by mixing with an organic compound. Fluorinated fullerenes, that is C60F60, they are known as Teflon bulls. Then this C60, since there are 60 carbons which are present, so there are 60 vertices, 32 faces. 32 faces means 32 pentagon and hexagonal faces, and a large number of symmetries. C60, it is a mustard color, and it looks brown and black as its thickness increases. The carbon-carbon bond length is of the order of 1.38 angstrom, and carbon-carbon single bond length is of the order of 1.45 angstrom. Now this C60, it also has a tendency of avoiding having double bonds within the pentagonal rings. which makes electron delocalization poor and results in the fact that C60 is not aromatic. And due to the absence of this aromatic character, fullerene behaves like alkenes and thus they undergo electrophilic addition reactions. Physically, these buckyballs are extremely strong molecules. They are being able to resist high pressure. They will bounce back to their original shape after being subjected to over 3000 atmospheres. Now these fullerene crystals, they are bonded weakly with each other by van der Waals forces. Coming to the applications of fullerene, it forms a superconductor when mixed with alkali metals. For example, K3C60 has been formed. Superconductors can be made by addition of alkali metals to these fullerenes. They take part in catalytic processes. Due to their therapeutic and diagnostic agent, due to size, stability and hydrophobic nature, therefore they are used as therapeutic and diagnostic agent also. They act as a potential inhibitor to HIV virus. They are used for trapping smaller size ions from solution of water. Because of their spherical structure, since there are no edges outside their only smooth surface, because of this spherical structure, they can be used as a lubricant. And the ball would act as molecular ball bearings. It can be used as a soft ferromagnet by reaction with tetrakis dimethylaminoethylene TDAE. If you mix C60 with TDAE, then they can be used as a soft ferromagnet. In addition to these applications, fullerenes, they are also used in electronics, microelectronics and optical devices. Thank you.